Okay, in this video we will solve a few problems from section 1.8 and 1.9. Basically, we will do, in this video we'll do problems about linear transformations, okay? So I would suggest that you pause the video before I start every problem, copy the problem, okay? Try to solve it by yourself, and then see how I do it. If you can do it, that's great. If you can do it, you can see how I do it. And but please pause the video, write down the problem, and try to solve it by yourself first, and then see what I have done. Okay, so we're given a matrix A, okay, and a linear transformation that's defined as T of x is equal to AX. Basically, A is the standard matrix of the transformation. T is 3 by 3 matrix. That means it takes vectors from R3 and brings them to R3. Okay, find the image. This is a very introductory problem. What does it mean to find the image of the vector 2 to 1 under T? Okay, so I have T of x is equal to T of the vector 2 to 1, but that's defined as the matrix A times the vector x, 2 to 1, or that's 1, 2, 0, 3, 0, 5, 0, 1, 0, 3, 0, 5 times the vector 2 to 1. You can express this as a vector equation, so 2 times the first column 1, 0, 3 plus second entry in the vector 2 times the column 2, 1, 0 plus the third entry, which is 1 times the third column 0, 0, 5. Or simply, by now you guys know how to multiply matrices, so we will have 1 times 2 is 2, plus 4 is 6, right? Unless I'm doing something wrong here. So 2 plus 4 is 6. Then I have 0. 0 times 2 is 0. 1 times 2 is 1. 0 times 1 is 0, so only 2. And then 3 times 2 is 6, plus 0 times 2 is 0, plus 5 times 1 is 5. 6 plus 5 is 11. Okay, and obviously I caught my mistake here. This is a 3 by 1 matrix. 3 by 3 matrix. This is 3 by 1. The product is going to be 3 by 1. Okay, so sorry about that mistake. Okay, or you can just say 2 times 1 is 2, plus 2 times 2 is 4, plus 1 times 0 is 0, so 2 plus 4 is 6. 2 times 0 is 0, 2 times 1 is 2, 1 times 0 is 0, so only 2, and then you have 11. Okay, the next question is determine if the vector B, given the vector B, determine if there is at least one vector in R3 such that T of that vector is equal to B. Okay. Well, here basically the question becomes, is B in the range of the transformation T? Okay. Or in other words, can B, this vector B here, can be expressed as a linear combination of the columns of the standard matrix A. But then we know how to answer this question, right? So we can say, is there an x, x1, x2, x3 such that A times x is equal to B, but A times x is equal to B is what? x1 times 103 plus x2 times 210 plus x3 times 005 is equal to the vector b. Okay? But we don't have to go through a vector equation. We know how to solve a matrix equation. Just create this augmented matrix and check whether it is check if it is consistent. So 210 005 augmented by the matrix 302. So I have row 3 minus 3 times row 1 is row 3. 1 2 0 0 1 0 0 and 3. 3 minus 3 is 0. 0 minus 6 negative 6. 5 minus 0 0. 2 minus 9, right? 2 minus 3 times 3 is negative 9. 2 minus 9 is negative 7. Okay, and now I need to eliminate this entry here. So row 3 plus 6 times row 2 is row 3. 1 2 0 3 0 1 0 0 0 0 5, and then here I have negative 7 minus 0 is negative 7. Okay, so because I have a pivot in each row, right, I don't have any I don't have a row here at the end that is 0 columns and then augmented by some non-zero entry. This system is consistent. So the answer to this question, is there at least one x such that this transformation brings x into B? The answer is yes, there is x in R3 such that t of that vector is equal to the vector b. If we want to answer what is that particular b, well, you just have to solve this. So if this is x1, x2, and x3, obviously 5 times x3 is equal to negative 7. So the last entry of x is negative 7 over 5. x2 is obviously 1 times x2 is 0, so x2 is 0, and x1 is equal to 1 times x1 plus 2 times x2, but x2 is 0, so x1 is equal to 3. So the particular vector x such that the transformation t becomes this given vector b is the vector 3 0 negative 7 over 5. Okay, so the next question is, for any vector b in R3, okay, is there x in R3 such that t of x is equal to b? Okay, this question basically, as the question is t and onto transformation, and t would be an onto transformation if the columns of the standard matrix A span R3. So the question here is, do the columns of the standard matrix of the transformation T, which is called A, do the columns of A span R3? And by that famous theorem 4, famous for it's called in this class theorem 4, the columns of A span R3 as long as every row is a pivot row. And as we can see here, right, if you look at just the matrix A, right, the reduced form of it or the echelon form of it, you can see that each row has a pivot. So yes, the columns of A span R3, which means T is an onto transformation. That means for each B in R3, there is an X in R3 such that T of X is equal to B. So the answer is yes, since the columns of A span R3. Okay. And the next question is, are there two different vectors, x1 and x2 in R3, where x1 is not equal to x2, so they're different vectors, right? Such that their images under the transformation T lead to a one vector B. Another question, is T a one-to-one transformation? But we know that the answer to this question is T a one-to-one transformation depends on the dependency of the columns of A. So again, A was reduced into matrix that looked like this, 1 0 0 0 1 0 0 0 1, and obviously the columns of A are independent, which means that T is a one-to-one transformation. That means for every single B in the image of the transformation, in the codomain of the transformation, there is only one X in the domain. So the answer to this question is no, there are no two different vectors x1 and x2 such that T of x1 is equal to T of x2 is equal to B, because T is a one-to-one transformation. Okay, so this is the second problem. A very short, easy problem. Let these two vectors be given. Okay. And then we define a transformation from R2 to R2 that maps X into x1 times v1 plus x2 times v2. Find the matrix A such that T of X is defined as AX. In other words, find the standard matrix of transformation. So we have T of X is equal to, by this definition, x1 v1 plus x2 v2, where v1 and v2 are given. So x1 times 2 and negative 3 plus x2 times sorry, this is v2, my bad, negative 5 and 2. Okay, so we know how to write this as a matrix equation. That's 2 negative 3 negative 5 2 times x1 x2, which is equal to A times the vector x. So obviously the standard matrix of the transformation T is just the matrix 2, -3, -5, 2. Question number 3. Let T be the transformation that's defined as a reflection through the line x1 is equal to x2, and then let S be the transformation from R2 to R2 that is a vertical expansion by factor of 3. Okay, find the following: the standard matrix of transformation for T, the standard matrix for a transformation S, and finally, right, the standard matrix for the transformation S composed with T. So for a particular vector, we first apply the transformation T, and to what are we going to get? We apply the transformation S. So what did we say? The standard matrix of transformation of a given transformation is consisted, the columns of this matrix are consisted of the images of the standard unit vectors under the given transformation. So when you approach this question, either you can remember the matrices that are given in the book, or you can just derive them based on what this particular transformation does to the unit standard vectors. So let's see what T does to the unit standard vectors. Okay, so in 2 dimensions, those are the vector, that's the vector E1, which is 1, 0, right? So the standard unit vectors 1, 0, and E2, which is 0, 1. Okay, so this is the vector E1, and here is the vector E2. So 1, 0, and 0, 1. Okay, and we want to reflect them over the line x1 is equal to x2. Okay, so if I reflect E1 over the line x1 is equal to x2, I will get E2. So that means that T of E1 simply becomes E2. So T of the vector 0, 1 becomes E2, right, which is 0, 1. And because 0, 1 is the image of the unit standard vector 1, 0, this here is the column, the first column of the standard matrix for this transformation. What happens to the vector E2 under this transformation? So that's the transformation of the vector 0, 1. So let's just see. This vector here reflected over this line becomes E1. So that's 1, 0. So from here, the standard matrix A for this transformation is simply consisted of the images of the unit standard vectors under this transformation. So 1, 0 became 0, 1, so 0, 1, and 0, 1 became 1, 0, so 1, 0. Okay, so that's part A. Part B, the transformation S is a vertical expansion by factor of 3. So we can apply the same idea here. This is E1, and this is here E2. Okay, if we apply vertical expansion of this vector, it's not going to move anywhere, it's going to stay here, right, because it's horizontal. So that means T of E1 is equal to T of 1, 0, and what do we get? Again, just 1, 0. So we got the first column of the standard matrix, the first column of the standard matrix of transformation for the transformation S. So sorry about that mistake. Here S. and then S of E2. So if we apply now a vertical expansion by factor of 3, we're going to end up at the vector. So E2 moves into the vector 0, 3. So that's S of 0, 1 becomes 0, 3. So let's call this matrix B is equal to 1, 0, 0, 3. Okay? And finally, part C. What is the standard matrix of the transformation as composed with T? So that means to a particular vector, first we apply the transformation T, and to what are we going to get? We apply the transformation S. So one thing we can do is just observe what happens to the standard unit vectors. So this is E1 and E2. So first we apply T. Okay, so E1 moves and comes here, right? So let's write the okay, so now this becomes T of E1, and under the same transformation E1 becomes E2. So now this here is T of E2. Okay, and now to these vectors we apply the transformation S. So this is 1, 2, 3 here. So S of T of E1 becomes this vector, vertical expansion by factor of 3, and this is not going to move because we don't have vertical expansion, so it's going to be the same as T of the S of T of E1 2. Okay, so let's see what happened to the, let's call this matrix C. Okay, so S composed with T of X is equal to the matrix Cx. Okay, and C is going to be consisted of the columns that are images of the standard unit vectors. So after applying these two transformations to the vector E1, to the vector E1, after the transformation T came here, T of E1, and then after applying the transformation S to this vector, to the image of E1 under T, we came here to the vector 0, 3. And what happened when we applied these two transformations to the standard unit vector E2? It just came to E1, so that's 1, 0. Okay, so this is one way of solving this. Another way, now that we know how to multiply matrices, this matrix here is going to be defined as the product of the matrix B times the matrix A. So be careful that we are keeping the order, okay? So first we applied the transformation T, that means its standard matrix is going to be to the right, and then its multiplication on the left by every consecutive transformation. So B times A, the matrix B is 1, 0, 0, 3 times matrix A 0, 1, 1, 0. Now we know how to multiply matrices. 1 times 0 is 0, plus 0 times 1 is 0, so the first entry is 0. 1 times 1 is 1, plus 0 times 0 is 0, 1 plus 0 is 1. 0 times 0 is 0, plus 3 times 1 is 3, and 0 times 1 is 0, plus 3 times 0 is 0. So as you can see, we got the same matrix C. Question number 4. Let T be a transformation that goes from Rn to Rm, defined by the standard matrix A, 1 to -3, -1, -2, 3, and let this line be defined. Okay. The questions are: determine the domain and the codomain of T. B. Find the image of the line under the transformation T, and describe as precise as possible the range of T. Okay. Okay, so A right away is a 2 by 3 matrix. This means that T is a transformation that takes vectors from R3 and brings them to R2. We can see this if I have a matrix A that's 2 by 3 and I multiply it by a vector, and the vectors are always column matrices, so by 1. In order this multiplication to be, this is a vector, in order this multiplication to be defined, these two numbers have to be the same. Okay, so obviously from here x belongs to R3, and then when this product is defined, we get a vector b whose size is 2 by 1, and from here obviously b belongs to R2. That's why the domain is R3 and the codomain is R2. Okay, so that's question A. Part B, I need to find the image of the line defined as V under the transformation T. Okay, so T is a linear transformation, so 3, 1, 1 plus T of -2, 1, 0 is equal to, since this is a linear transformation, this is T of 3, 1, 1 plus T of T times -2, 1, 0, which is equal to T of 3, 1, 1 plus, pull out the weight, T times the transformation of the vector -2, 1, 0. Okay, but the standard matrix of the transformation is A, so this is defined as A times 3, 1, 1 plus T times A times -2, 1, 0. And the A is 1, -1, 2, -2, -3, 3 times, 3, 1, 1 plus T, the matrix A, 1, -1, 2, -2, -3, 3 times the vector -2, 1, 0. And then just compute this, we'll get a two-dimensional vector. 6 plus 2 is 8, minus 3 is 3, plus 2 is 5, minus 3 is 2, my bad, 2, and then -3 minus 2 is -5, plus 3 is -2, plus T times 2 times -1, 1 times -2 is -2, plus 2 times 1 is 2, -2 plus 2 is 0, 3 times 0 is 0, so 0, and then -1 times -2 is 2, -2 times 1 is -2, 2 minus 2 is 0. Okay, so we just get the vector 2, -2. Okay? this is a step-by-step solution of this system, of this question. You would get absolutely the same question if you just expressed v here as 3 minus 2t, right? 3 t times negative 2 is negative 2t, so that's 1 plus 1 times t is 1 plus t, and finally 1 plus t times 0 is 0, so only 1. Okay, and then so I'm doing the same question. T times v is equal to a times v, which is equal to 1 to negative 3, negative 1, negative 2, 3 times, and then what we got here, 3 minus 2t, 1 plus t, and then 1. And now what do we get? 1 times 3 minus 2t, that's 3 minus 2t, plus 2 times 1 minus t, that's plus 2 plus 2t, minus 3. And then negative 1 times 3 minus 2t, that's negative 3 plus 2t, negative 2 times 1 plus t is negative 2 minus 2t, and finally 3 times 1 is 3. So these are out, negative 2t and 2t, positive 3 and negative 3, so I get 2. And the same thing happens, negative t and negative 3 cancels, 2 and negative 2t cancels, so I get only negative 2. So as you can see, these two answers are the same. Okay, and at the end we have to describe the range of t. Okay, so I know that the codomain is R2, so what is going to be the range? What is going to be the image of the domain? Is it all of them, all the vectors in R2? In other words, do the columns span R2? Or is it a line in R2? Okay, so let's see. I want to find all the vectors. So this is C. Find the expression for all the vectors B in R2 such that AX is equal to B. Okay, or in other words, I have here the matrix A, 1, negative 1, 2, negative 2, negative 3, 3, augmented by B1, B2. Well, in order to reduce this matrix, it's very simple. It's just R2 plus R1 becomes R2. Then I get 1, 2, negative 3, B1. And then when you add all of these entries, you just get 0. And then B2 minus B1. Okay? Well, in order this system to be consistent, we need B2 minus B1 to be equal to 0. Sorry, I made a mistake. I added the two rows, so this is plus. So B2 plus B1 to be equal to 0, or simply B2 to be equal to negative B1. So for any vector x in R2, okay, the following must be satisfied: that x2 is equal to negative x1. Okay, so that means that any vector that is in the image of this transformation is going to be simply x1 negative x1, which is x1 1 negative 1, okay, which is nothing else but the line spanned by this vector, the line spanned by the vector 1 negative 1, this vector right here. But what is that line spanned by this vector? Sorry, that's the line y is equal to negative x. So the range of this transformation is the line y is equal to negative x, or x2 is equal to negative x1. Okay, and now we need to show that this transformation is not a linear transformation. In order to show that a transformation is a linear transformation, we have to show that t of 0 is equal to 0 and t of cv plus c1v plus c2u is equal to c1t of v plus c2t of u. Okay, so the question asks us, show that it is not a linear transformation. Okay, so that means that one of these two conditions definitely will fail. Okay, so let's check the first one. So t of the vector 0, 0, right, it's r2 to r2 is equal to, so x and y are zeros, and by following this definition I get 0 plus 2 times 0, obviously that's 0, and absolute value of 0, which is 0 minus 0, it's also 0, so I get the 0 vector. So the first condition is satisfied. Now I have to, that means inevitably, because the question says show that it is not a linear transformation, that means that this condition here will fail. So now you have to take two vectors, okay, where this equality will not be satisfied. Okay, so let's take the vector, let v be equal to the vector negative 1, 1, and u be the vector 1, negative 2. Okay, then t of v, which is t of negative 1, 1, so now I just follow this definition. X is negative 1, so negative 1 plus 2 times 1 over absolute value, so not over, sorry, and in the second entry absolute value of x, so absolute value of negative 1 minus 1. Okay, so what do we get? Negative 1 plus 2 is 1, and 1 minus 1 is 0. Absolute value of negative 1 is 1, so 1 minus 1 is 0. Now t of u is equal to t of 1 and negative 2 is equal to, so x is 1, 1 plus 2 times negative 2 by this definition. And in the second entry is absolute value of 1, which is 1, minus 2, which is equal to 1 minus 4, and 1 plus 2, so that's negative 3 and 3. Okay, now of course if we take the weights here, c1 and c2 being 1, we need to show that the following will fail. T of v plus u that it will not be equal to t of v plus t of u, right? This is a condition that shows that a particular transformation is linear transformation, but we want to show that this is not a linear transformation. Okay, so t of u or v plus u, doesn't matter, plus u is equal to t of, well, what is v plus u? Negative 1 plus 1 is 0. 1 minus 2 is negative 1. That's equal to, by this definition, that's equal to 0 plus 2 times negative 1, an absolute value of 0 minus negative 1, which is equal to negative 2 and 1. But this is not equal to t of v plus t of u, and these two vectors are t of v is 1, 0, plus t of u is negative 3 and 3, and the answer is negative 2 and 3. So obviously, since this condition fails, t of v plus u is not equal to t of v plus t of u, then we conclude that this is not a linear transformation. So when you're asked to prove that something is a linear transformation, you have to prove these two conditions. You have to prove them, right, for any two matrices. If you're asked to show that it is not a linear transformation, then you have to show that either one of these two conditions fail. Okay, so you just have to show that they don't work for just two vectors, and then you're done with that proof.